All right, let's talk about something you hear all the time: encoding, encryption, and hashing. These words get thrown around a lot, sometimes like they all mean the same thing. But they don't, not even close. In fact, they're completely different tools for totally different jobs. And mixing them up, well, that's not just a little technical slip-up. It can blow a huge hole in your security. So today we're going to set the record straight, once and for all.
So here's our game plan. First, we'll look at the big picture problems these tools are built to solve. Then, we'll zoom in on each one. Encoding, our data translator. Encryption, the digital safe. And hashing, the unique digital fingerprint. After that, we'll put them head to head to see how they stack up. And finally, we'll talk about why picking the right tool for the job is just so incredibly important.
Okay, so before we dive into the nuts and bolts of how these things work, we really need to understand the why. You see, our data is constantly facing different kinds of challenges, and there's no single magic bullet that solves everything. You need a whole toolkit.
And really, this is the core question, isn't it? It boils down to these three things. We need our data to be usable, so all our different computers and systems can actually read it. We need it to be secret, so prying eyes can't see what's inside. And we absolutely need it to be trustworthy, so we can be sure that nobody's messed with it. Three very different needs, which means we need three very different tools.
So let's kick things off with our first tool, encoding. And for this one, I want you to just forget about security for a minute. That's not its job. Encoding is all about solving one problem and one problem only, making data usable and compatible. It's a translator, pure and simple.
The thing to really get about encoding is that it's a totally public process. There's no secret key, no hidden magic. It's just a standard, well-known way to change data from one format into another, so it can travel smoothly through systems that weren't designed to handle it in its original form.
And this right here is the classic problem encoding was born to solve. Think about the early days of the internet. A lot of the protocols, like the one for email, were built to handle simple text. That's it. So, what happens when you want to send a photo or a PDF? You can't just cram that raw data into the system. It would just break. You need a translator to turn it into something the system can understand.
And you actually see this kind of translation happening all over the place every single day. That attachment you just sent in an email, yep, it got encoded with something called base 64. You ever see a tiny little icon on a web page that loads instantly? That's probably a base 64 encoded image right there in the code. Even those super important SSL certificates that keep your browsing secure, they're often stored in a base 64 format so they can be easily handled as text.
Now, this is probably the most important thing to remember about encoding. It's so easy to look at that jumbled mess of characters and think, wow, that looks secure, but it's not at all. It's just a disguise. It's like taking the word hello and writing it out in Morse code. It looks different, sure, but anyone who knows Morse code can read it instantly. It's a format change, not a secret.
Okay, on to tool number 2. This is the one that's all about security. If encoding is the public translator, then encryption is the lockdown digital safe. It was designed from the ground up for one mission: keeping your data secret.
And here's the game changer, the key. Unlike encoding, which is an open book, encryption is a two-way street that's completely guarded by a secret key. The entire goal here is confidentiality, to scramble your data so thoroughly that it's just gibberish to anyone who doesn't hold that specific key.
This diagram shows it perfectly. You start with your normal, readable data, that's the plain text. You mix it with a key and run it through an encryption algorithm, and out comes unreadable gobbledygook, the ciphertext. But here's the magic. If you have the right key, you can reverse the process, that's decryption, and get your original data back, good as new. What gets locked can be unlocked.
Now, it turns out there are a couple of different ways to handle these keys. With symmetric encryption, it's pretty straightforward. Both sides use the exact same secret key to lock and unlock the data. It's super fast. Then there's asymmetric encryption, which is a bit more clever. It uses a pair of keys, a public key that you can give to anyone and a private key that you keep to yourself. Anyone can use your public key to lock a message, but only you can unlock it with your private key.
All right, time for our third and final tool, hashing. Now, I want you to throw out everything we just talked about, because hashing is a whole different beast. It's not about usability, it's not about secrecy. Its one and only job is to guarantee integrity. It's like a unique digital fingerprint for your data. The key phrase to burn into your brain here is one-way function. Hashing is designed, on purpose, to be a one-way street. You can't go back. You can't unhash something. You feed data in, any amount of data, and you always get a fixed size string of text out. And if you change even a single bit of that input data, you get a completely different hash on the other side. So what's this good for? Well, the perfect example is passwords. A secure website never, and I mean never, stores your actual password. When you sign up, it takes your password, puts it through a hashing function, and stores that resulting hash. That's it. Later, when you go to log in, it takes the password you just typed, hashes it the exact same way, and then just compares the two hashes. If they match, the system knows you have the right password and it lets you in, all without ever having to store the original vulnerable secret. Pretty smart, right?
So what makes a hashing algorithm something you can actually trust? Well, it has to have these three critical properties. First, it needs to be collision resistant. That just means it's basically impossible for two different files to produce the same hash. It's like fingerprints. No two should be alike. Second, it needs pre-image resistance. That's our one-way property again. You can't start with the hash and figure out what the original data was. And third, there's second pre-image resistance, which means if a bad guy has a file in its hash, they can't create a different malicious file that sneakily has the same hash.
Whew, okay, we've looked at them one by one. Now for the main event. Let's put these three side by side in a showdown to really make the differences stick.
And this table really is the whole story in one spot. Check it out. Purpose? Encoding is for usability. Encryption is for confidentiality. Hashing is for integrity. Reversibility? Encoding can be reversed by anyone. Encryption can only be reversed with the key. And hashing? It's not reversible. Period. And the key question, pun intended, is a dead giveaway. No key for encoding or hashing, but a key is absolutely essential for encryption. If you're going to remember one thing from this whole explainer, this table is it.
So, now we've seen how different these tools are, which brings us to the most important part, why getting this right is so critical. Using the wrong tool for the job isn't just inefficient, it can be a total disaster.
You might be thinking, okay, I get it, they're different, so what? Well, why does this matter so much? Because in the real world, these aren't just abstract ideas. Choosing wrong has very real and very serious consequences.
Just look at these classic blunders. You use encoding to protect sensitive data? You've done nothing. Your data is sitting there in plain sight for anyone to read. You hash a file that you need someone else to actually use? Well, too bad. They'll never get the original file back. And maybe the scariest one, you encrypt your user passwords instead of hashing them. If a hacker steals that one encryption key, they can instantly decrypt every single password in your database. Game over. And that leads us to the final #1 takeaway. It's so simple, but it is everything. Match the tool to the task. If your goal is to make data work across systems, you encode. If your goal is to keep data a secret, you encrypt. And if your goal is to prove data hasn't been tampered with, you hash. That's it. So I'll leave you with a thought. The next time you're browsing online, think about it. That little lock icon in your browser, the way a website remembers you're logged in, that picture you just attached to an email. Now that you know what to look for, where can you see encoding, encryption, and hashing working behind the scenes, often all together, to keep your digital world running? Thanks so much for joining me.